Just take, okay. So this is our group, lesson 6 group work problems. And I'm going to start off with number 1. So for number 1, they're asking for 1A, they're asking what is the frequency of the recessive D allele in this population. So what you do is you take the square root of 1 out of 150,000, giving you a value of 0.0026, and that is the frequency of the little d allele. For B, it's asking you what is the frequency of the big D allele, and then what you just do is you take 1 minus 0.0026, and that gives you 0.9974. For the C, what is the frequency of the homozygous dominant genotype in this population? So that is also the p-square value. So what you would do is you take the value of p, which is 0.9974, and you square it, getting a total of 0.9948 or 0.995, depending on how you round. And then for D, what is the frequency of the heterozygous genotype in this population? And the heterozygous is the 2pq in the Heidi-Weinberg equation. So what you do is you take 2 times 0.0026 times 0.9974, and that equals a total of 0.0052.
For question 2, the term in the Hardy-Weinberg equation that represents the frequency of the IB allele is q squared, while the term in the Hardy-Weinberg equation that represents the frequency of IA-IB genotype is 2pq. For B, the DeGeorge syndrome is an autosomal dominant disorder that affects 1 in 4,000 individuals in the human population. The 1 in 4,000 individuals in the population affected by DeGeorge syndrome is represented by the p squared and the 2pq terms in the Hardy-Weinberg equation. In reference to question B, 3,999 out of the 4,000 individuals of the population unaffected by DeGeorge syndrome is represented by the q squared terms in the Hardy-Weinberg equation. In D, the r squared term in the Hardy-Weinberg equation best represents the frequency of the MD allele. In E, in reference to the previous question, the 2pq terms in the Hardy-Weinberg equation can represent the genotype of a duck with restricted plumage. The human disease sickle cell anemia is a result of a SNP. Monomorphic is a term that describes a trait that produces a single phenotype in 99% or more of the population. And DEANS is another name for a local population. And the MHC genes in humans are highly polymorphic. So for 3, let's see here. The frequency of the non-disease allele in the human population, what you would do is that would be your Q value. And so you take the square root of 1 in 6,000, 1 divided by 6,000, and that would give you your Q value. And then the frequency of the non-disease allele, what you do is you solve for 2pq, and you get an answer of 0.99992. For B, the frequency of Marfan syndrome allele in the human population would be your p squared and your 2pq values, and that would end up being 0.0000008. Yeah. For C, the frequency of heterozygote individuals in the population would be your 2pq value, that would be 0.00016. And then out of a population of 5 million people, how many heterozygotes are expected? And so you would take your 2PQ value, which is 0.0016, and you would multiply it by the 5 million, and you'd get 850.
All right. Okay. For question 4, this wonderful man named Jeffrey and his friend genotypes for the enzyme peroxidase in pine trees in Colorado. Sounds like a fun trip. So for A, it says determine the allele frequency of the R squared and R cubed alleles. So here for the genotypes listed, so we've got R squared, R squared, R squared, R cubed, R cubed, R cubed. So we've got corresponding values would be for P, 2PQ, and Q squared respectively. So in order to find the R squared value, you take 2 times 135 plus 44, and then you divide that by whatever 2 times 180 is, which is 360, or 180, sorry, 190. That's total individuals. So 380, excuse me. So your value for R squared, which would be equivalent to P, would be equal to 0.8263. Now you go about finding R cubed the same way. So you go 2 times 11 plus 44 over 380. That gets you the 0.17368 equivalent of the Q value. So in order to go through, we go through and we find the P squared value, which is equal to 0.8263 squared, which is equal to 0.6827-ish. You go in and you take your Q value and go ahead and square that for Q squared, which is equal to 0.17368 squared is equal to 0.030165. And you go through and you calculate 2PQ, which is equal to 2 times 0.8263 times 0.17368, gets you a value of 0.2870. Okay, the next step you got to go through in order to determine the chi-square value is you've got to find the expected number in concordance with the expected number of individuals, or in this case trees, in the population for each ratio. So for P squared, you take that P squared value, which is 0.68277, multiply that by the total population, which is 190. So you get 129.73 trees. You take the Q squared value of 0.030165, multiply that by 190. You get approximately 6, or 5.73. And then you take the 2PQ value, which is 0.2870, multiply that by 190, you get 54.53. Now with those expected values and the observed values, you go ahead and you plug and chug in the chi-squared equation. So after you get that, you get the grand total of, so for example, I'll do the first one. For P squared, you take the observed value minus the expected, which is 135 minus 129.73. So that would give you about, and then you divide that by 129.73. And that gets you the decimal answer of 0.21408. Now, respectively, you would go through for each genotypic class, plug in the expected minus the observed value, square that over the observed or was that, yeah, over the, or that expected value? Did I mix my stuff up? Either way, you stick that into the chi-square equation, and it will pop out a chi-squared value of 7.0. Was it 7.09 or 7.06? Yeah. Okay. But anyways, it's in there, and interpreting the chi-square value. So our determinant on our chi-square value. This means, since we have this value, it means that we can reject our null hypothesis, meaning that these trees are following Hardy-Weinberg equilibrium.
Okay, so problem 5 is a little more expansion on the Hardy-Weinberg. You're adding, there's 4 different alleles with decreasing and increasing dominance. So the question A is asking for the frequency of the chinchilla dog, of a pale gray dog, and of an albino dog. And so in that order is 0.3873, 0.075, and 0.6083. For B, among the population of 2,000 dogs, how many you would expect to have pale gray phenotype and yet be heterozygous would be 150. For C, population of 5,000 dogs, how many you would expect to have a white coat and dark eyes, but also heterozygous would be 920. And for D, a population of 15,000 dogs, how many would you expect to be chinchilla or albino? And the total is about 3,113 dogs.
Okay, and those are group work problems. Thank you all. See you next week.
Thank you.